Hi, my name is Dana Golden. Welcome back to a discussion of commodity markets, and today we're going to be looking at commodity market supply. So commodity market supply is fundamentally physical. These goods have to be moved around the world. You're not like just sending packets of information over the web. Commodity market supply is based on shipments, and so you'll often hear about in these markets the limitations of rail and the limitations of cargo ships. You have to ship very specific items long distances from where these things can be created to where they're used. We have increasingly global supply chains, and maybe in the future decreasing global with some new changes in globalization. So limited progress differentiation means that almost all competition comes down to cost structures. This is almost entirely perfect competition in terms of there's no differentiation, everything is the same, so it really is about how much things cost and how easy it is to ship, but also really the marginal cost of the producers determines who's going to succeed in the market. So the classic model of commodity market supply is the hoteling model, which allows you to think about optimal production of a non-renewable resource. It demonstrates equilibrium from a price-taking firm operating in a market with no product differentiation and non-renewable resources. Consider the owner of a mine optimizing the supply of resources from a single mine. How do you choose how much to extract? It's a cake-eating problem. Eat all the cake for today or save some for tomorrow. This is a very traditional macroeconomic problem, but it's a problem in this case in industrial organization and environmental economics, the hoteling model. Here's an open pit mine. You have to figure out how much of this is going to mine today. It's going to run out sometime, so how are we going to save it to make sure we are profitable over the long term, given that we don't have an infinite amount. Some assumptions of the hoteling model: the amount of commodity in the mine is known and fixed. Commodity is perfectly homogeneous with constant marginal process of production and extraction. By the way, you can change any of these assumptions, and we will change the model in significant ways. So this is a very useful exercise that I might actually do on one of the homeworks. Just think about, how would the hoteling model change if we changed these assumptions? How would the hoteling model change if we changed the interest rate? How would the hoteling model change if we made it so there were different marginal costs of extraction? Producer has perfect control over the rate of extraction. They can choose exactly how much they want to extract. And the quantity demanded is downward sloping linear function of price. There is a single constant interest rate on capital set by the market. So again, the implications: hoteling's rules provides insights into price paths for exhaustible resources. Scarcity increases over time, pushing prices up. The model helps inform policy on extraction, taxes, and sustainability. So some assumptions of the model: the resource is finite and exhaustible. You have a total stock S. You have tier periods 1 and 2 with discount rate R. You have price P of T, which depends on the demand function D of QT, where Q of T is the quantity produced in period T. Profit maximization is subject to intertemporal constraint on resource use. So maximization problem: you maximize the discounted profits over 2 periods. Maximize with respect to Q1, Q2 of pi, where pi equals the price of the current quantity times the quantity plus the price of the quantity in the next period times the quantity next period over 1 plus R. And then you have a resource constraint: Q1 plus Q2 is less than S. You can't mine more than the total supply because it's a non-renewable resource, and both of them are less than 0. You can't put more lithium back in the ground. So hoteling's rule, which is very common in macroeconomics, you'll see versions of this. It's just the solution to an intertemporal order constraint. Hoteling's rule suggests that the resource price net of extraction costs grows at rate R. Owners allocate resources such that the marginal profit each period is equal in present value terms. So the derivative with respect to price of the quantity period 1 over the derivative with respect to price in period 2 is equal to 1 plus R, and this ensures that the intertemporal profit maximization extraction path is followed. So pretty crucial to you needing to mine in both periods is that you as a miner face a downward sloping demand curve. So this is not assuming a perfectly competitive market, but it's kind of more accurate to the world most people lived in at the time that this model came out. And yeah, still pretty accurate that you can't pump out infinite amounts of a good. So you set effectively the prices, the marginal profit in each period, the ratio is equal to 1 plus R. So you solve the model, you derive P1 of Q and P2 of Q from the demand functions. You substitute this into the profit functions, and you differentiate with respect to Q1 and Q2. And you solve first-order conditions for optimal Q1 star and Q2 star. So numerical sample, assume linear demand PT of QT equals A minus B QT. Set parameter values and solve for Q1 and Q2. Example parameters, A equals 10, B equals 1, X equals 10, R equals 0.05, straight to 0.5, and then you can solve for Q1 and Q2 using the hoteling rule. So you can also have a multi-period hoteling model. You extend the two-period model to T periods, allowing for more realistic representation of resource extraction over time. And you can maximize the discounted profit stream over T periods. So you have a series of quantities that you're choosing, and then you have a sum of profits discounted by R. We talked about discounting earlier on in the class in our cost-benefit class. And then you're subject to the resource constraint that now it's not just the single period or the two periods where you have to have quantities less than the total supply. The total quantity must be less than the total supply. And so if at some point you've used all your quantity, you're now done and the mine has to close. So Taylor's rule in a multi-period context, price of net extraction cost grows at the rate of discount. So in theory, you should extract a little bit over time, and then the price net extraction should grow. The marginal profit should grow at the rate of interest. This is the theory for why commodities prices tend to go up over time, is because you have less of them, and because you're discounting at the rate of interest. The prices increase over time, reflecting growth and scarcity. This isn't exactly true. There are reasons why this isn't true, but this is pretty true. And then optimal extraction path smooths profits, balancing future and present values. Yeah, this is a thing you see basically in every macroeconomic model. More common models with individual agents because they have utility functions, but you see this even in this model, is that actually the answer is that things decline pretty smoothly. You're not deciding to eat all the cake today and leave no cake for tomorrow. Most problems end up being you have a little bit of cake each period, which is what we see in reality. So what happens if you relax some of the assumptions? So what if there is another technology? So another resource available to fixed price. This provides an alternative to resource depletion. Now, instead of running out of the entire resource, if it becomes too expensive, you move away from this. We see this a lot in real life. Coal is an example where actually coal just became too expensive, and so the United States stopped using it. That's partially due to regulation, but partially not. Whale oil partially became too expensive. So the impact, this creates a price ceiling. The resource extraction price cannot rise above the cost of the backstop. Finite resource extraction, resource owners may accelerate depletion to extract value before substitution. And the transition to the backstop technology determines the long-run market outcomes. So this is something you see in a lot of markets. You see temporarily there's a price shock, and then this leads to investment in backstop technology. The backstop technology becomes cheaper, and you see in the long run, now the backstop technology is taken over. This was fundamentally a big part of OPEC's failure in the 1970s through the 2000s, when they kept using oil price as a weapon. They kept saying, we're going to raise the price of oil if you don't do what we want. They were using geopolitical prices as a weapon. And then this made it profitable for, guess what, the United States to invest in fracking and everyone to buy Toyotas and small cars and go electric. And now OPEC is kind of in a bad situation. OPEC is trying to lower supply. They're trying. Saudi Arabia is like, come on, guys, let's get together and raise the price of raising supply. It's just not working. And Angola and Nigeria are like, What are you doing? You're only quickening our demise by, or do you not understand that we're already irrelevant because of the backstock technology? So it's telling us really useful, valuable impacts and implications for the real world, and helps to explain a lot of events, including geopolitical events like Angola leaving OPEC+. So relaxing hoteling assumptions, you have variable mine quality. Resource deposits differ in extraction cost and quality. So you have cost heterogeneity. Low-cost deposits are extracted first, and extraction costs rise over time as higher cost deposits are utilized. So now the prices rise faster than the discount rate to reflect that there's an increase in cost because the low-cost deposits have already been extracted. So now, as you move on through time, you extract higher cost deposits. This is certainly what happens with rare earth metals and most metals over time, is that you have the easy mines cut first, and then over time people come up with ways more and more creatively to extract more and more minerals. And then the supply curve becomes steeper, influencing market responses to demand shocks. And the last one we'll talk about in terms of relaxing hoteling assumptions is market power. So maybe a single producer or cartel controls a significant portion of the resource market. This was the case for a long time with OPEC+. You're seeing some attempts to make this happen in the metals market. You, at times, have seen cartelism in various places in the agricultural market, though it's not very common because it's very hard to have a crop where you have that much market power. What ends up happening is you have price markups. Producers restrict output to increases of prices above marginal cost, to increase prices above marginal cost. You extract resources at a delayed level to maximize present value profits, and then market outcomes deviate from socially optimal extraction paths. OPEC, has collusion and strategic behavior, and implementing these mathematically into the model I showed you before is left as an exercise to the watcher. So next we're going to talk about Hubbert's model of resource depletion. This was developed by geophysicist M. King Hubbert to model the production cycle of a finite resource. So in hoteling, you're going to have a relatively smooth path. You're just going to make less and less, and then eventually you run out. But you're pretty much going to smooth yourself. In Hubbert, basically the idea is that production follows a bell curve shape over time. And this is where the idea of peak oil comes from, is the idea that you start off mining a little, and you mine a lot, and then you go down. So resource extraction starts slowly, accelerates to a peak, and then declines symmetrically as resources become depleted. So this explains the idea that some commodities become valuable, they become important, and then they fall away. This is probably not as relevant to agricultural commodities where we've been using corn and wheat for thousands of years, but it's very relevant to oil fields and metals mines. People used to think this was a good model of a commodity as a whole, but it's actually much more valuable for an individual resource, which is why it's often applied to oil fields where production initially rises with new discovery and technological improvements, and then peaks and declines. When the peak signals a maximum production rate, and then after that, extraction becomes increasingly difficult and costly. So mathematically, Hubbert's curve is modeled using a logistic function to represent production over time. You have QT equals Qmax, and then it increases slightly, and then it goes down. So that you have a total resource available, which is Q of T. This is how much you can recover. So it's not how much is in the ground, but it's how much you can get out. And then you have this curve that goes up and then down. And then you have B, which is growth rate of production, which is how much more of the, which is basically in this model represents how much more you're going to need. It's a demand factor. So the peak production time occurs when Q of T reaches maximum rate around the T equals A over B. Around the peak, production time decreases as remaining resources become harder to extract, leading to higher costs and lower yields. This is kind of an odd economic model. It's a very geophysical model. There aren't a lot of decisions being made here. It's just kind of trying to model behavior, as opposed to telling, which is a very, very obvious economic model. So here's Hubert's peak for oil. So I think this is oil. I don't actually remember which commodity I grabbed this from. But you have cumulative production. This is provable reserves. And this is this idea that's just going to go down and fall. And so this is something I want you to remember if you ever choose to go into the commodity space. Every day, your commodity is dying. When you wake up in commodities, not so much in agriculture, sometimes in agriculture, but definitely in metals and energy, you should wake up today and think, one day people are not going to need natural gas anymore. One day people are not going to need lithium, and if they still do need lithium, we're going to be out of it, so tough turkey for you. Every day, there's less and less of your commodity. There's less and less to go around, and one day your industry is going to be dead. So you've always got to be thinking about how to squeeze out more of the commodity from the ground, and you've always got to be thinking about what's the next thing. If you're thinking about right now, I want to get into coal. Don't. I don't care if coal's your passion. Read up on natural gas. It's not that different from coal. Read up on solar. It's not that different from coal. Figure out like what the commodity is going to be in 10 years. Not today, because over time, commodities change, and you have to grow with the change of the commodities. Otherwise, just like every day the commodity is dying, every day your career will be dying. So here's Hubbert peak in oil. Hubbert peak worked really well in the United States until the early 2000s. So we had this increase roughly following this bell curve, and then we peak, and then we went down. And then what happens here? Fracking happens here. So we see this fracking, and we broke down the Hubbert's curve because of the shale revolution. Markets are incredibly good at reacting to price rises. Never underestimate how good markets will be at finding ways to get more oil and more metals out of the ground, because the market really understands that how profitable these are, and someone will figure out a way to make that it could happen. So the industry cost curve is the final mathematical type on commodity market supply. It's a graphical representation of the supply side economics of commodity markets. It ranks producers based on their production costs from lowest to highest and plots the cumulative production against cost. So you have fixed costs, infrastructure and equipment, variable costs, labor, raw materials and energy, and capital costs, investment for capacity expansion. And you have producers' margins. Producers with lower costs operate profitably at even lower prices. And then high-cost producers are vulnerable during price declines. Price is determined by the cost of the marginal producer. Highest cost producer is still active. Later on, we'll talk about electricity markets, and we'll talk about LMP, which is location marginal price. That is just an industry cost curve. So, like, the entirety of electricity markets is just industry cost curves. So this is the global oil production cost curve. You have over here the already produced, someone's just waiting to sell. Then you have Middle East and North Africa who are waiting in the wings, going to come in. And then you have other conventional oil. And then you have the Arctic. You have light, extra heavy oil and bitumen. You have light, tight oil. And then right over at the side here, you have cold oil, which is not cheap or easy, but is possible if oil prices got high enough. Because here you have the price. Here you have the remaining recoverable resources from the suppliers. And so if prices of oil go high enough, you will start turning coal to oil. I don't anticipate that's ever going to happen in the near future. I think we're probably going to be declining in oil for a long time. But yeah, always think about what's going on with this production cost curve and who is the marginal producer, because that's the person who's going to set the price. And I hope you have a great day. I hope you learned something, and I'll leave it there. Thank you.